Okay, I should be live. Welcome. I don't know if there is going to be anybody today. In the US, it's a Thanksgiving weekend, so I assume that I'll be by myself, but that's fine. Okay, I'll wait a couple of minutes to see if anybody joins while I check that everything works. Hmm. Okay, so what I thought I'd do today, I would just go through the list of open problems on the website that has been sitting there for years and just relook at it and clean it up, essentially. And so, how do I do this? Blah, 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 blah. So I would probably be useful to have the list on the website open in one window, which is going to be slash problems. Okay, so if anybody wants to look at it, can I put this in the chat? Yeah, so that's the list of problems on the website. And I'll go through them and make sure that they are still relevant, and if not, to modify them and so on. And if people have questions, people are online. Oh, there you go. Tobias is actually in, and Mark is actually in. So I'm not going to be by myself. Very good.
Hi.
Hi.
Hello to both. And somehow the audio didn't go where it was supposed to go. Why is it? Okay, let's see if this works. Okay, fine. Okay, so that's the thing. And let's see if I can share this window here. There we go. Did it show up?
Yep.
Okay, hopefully it's readable. Okay, so let's do this. And again, since the purpose is to make these problems intelligible, if they're not intelligible, please let me know and I'll try to fix it. Okay, so the first one is classical mechanics as a high entropy limit of quantum mechanics, category quantum information, category quantum mechanics, quantum information, classical limit and entropy, prove or dispute the following conjecture: a sufficiently high entropy state can be approximated by a statistical mixture of Gaussian wave packets. Actually, the thing is going to be so the mathematical process. So this is basically done because we have the paper out on the archive that it's now submitted for publication. So how do I? It doesn't make sense. Does it make sense to let's see? I would say solved somehow. This I will need probably something to indicate which problems are solved or not. So we'll need another tag here, like open or closed. If I had like a good issue tracker, I would just use an issue tracker. But the problem is that we need equations, and that doesn't work so well with issue trackers. Oh, and I need my local Jekyll running so that I can see that the page actually works. Okay, let me do this, and I need the local website. So 4,000. Okay. So does it even make sense to review this? Area can be approximated by a statistical, classical, I would just say the classical statistical mixture. And then mathematical derived, so this, I'm actually not doing it in this way. I can say this is the old characterization of the problem. I'll just leave it. So the figure significant problem is the same. The idea is to show that the classical limit arises when a physical mechanism, not but just as an approximation. A single particle in a pure state will have low entropy, and therefore the approximation will fail. A gas of multiple particles at room temperature, well, we have a high entropy, and therefore it can be approximated with a classical mixed state. While we will commit an error in making the approximation, the idea is that such an error will be below the uncertainty associated with the high entropy. The conjecture is motivated by observing that pure quantum states have zero entropy, while pure classical states, microstates, have minus infinite entropy. They are a point over a continuum, therefore a set of measured zero. The lower bound for entropy is also established by the third law of thermodynamics. Elastic mechanic states and quantum mixed states then must diverge as the entropy decreases, since they cannot go to zero in the same way. Okay, so I would say maybe as a first thing, we should say problem solved. Let's see, there's a preprint at and we can put the location of the preprint, which is this. And how do I make links in like that? So I just do this, 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 and this. Okay. Now, and now if I look at in the draft here, all right, so it would be nice to have something that tags these things a little bit better, but for now, let's just do it like this. All right, so this is done. A classic uncertainty. Find out how to generalize the uncertainty relationship we found for classical mechanics, as it can be seen, for example, in this paper. Mathematical problem in the nutshell, the problem is equivalent to studying the evolution of the covariance matrix over phase space, a symplectic manifold, under a possible linear Hamiltonian evolution. That is under the symplectic group. And as an example of the type of things we're looking for, if we start with a packet with no correlation across degrees multiple degrees of freedom and equal uncertainty within each degree of freedom, a condition related to thermodynamic equilibrium, do we find that the uncertainty in each degree of freedom cannot become lower than the initial one? If starting from the previous case, is it true that the uncertainty within a degree of freedom can only increase if you're adding a correlation to another degree of freedom? Does it mean that the equipartition of entropy over uncorrelated degree of freedom is the lowest bound? Physical significance. The idea is to explore more in general the relationship between information theory, Hamiltonian mechanics, and thermodynamics. The conjecture is that Hamiltonian dynamics preserves the entropic relationship that one would find at equilibrium. The classical uncertainty principle is essentially an interplay between the total uncertainty, which is conserved, and the ones along the individual variables, which can be increased by introducing correlation between them. This work needs to understand the interplay between the total uncertainty and that of each degree of freedom. So this still makes sense. I have the video of this, and so it would be nice to add it. Does the template allow for a video. Let me see. How did that work? Where are the layouts? Problem. La, 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 la. Yes. So if I go here and look at my list of videos, and I had the one, how does insanity propagate, right? This one. So if I copy this, get shareable link, and I do video, and I put this here, and then I go and look to my preview. Do I get the right thing? Problems. I forgot to open this page. Okay, so almost there. To protect your security, YouTube will not allow Firefox to display the page if another site has embedded it. To see this page, you need to open it in a new window. Why do I have, what? Yeah, but the other embedding are working, so why does this not work? Okay, well, I'll need to figure it out, and no time like the present. So I have a videos here. So somehow these work, right? If this is working, why is this template not working? And now we play spot the difference. This looks the same. Iframe style width, position absolute. There is a max height. And the rest looks the same to me. Okay, well, this is not easy to debug then. It will be left later to do something this afternoon. Okay, so this is still a problem. Then characterize the tensor G alpha beta gamma. Characterize the geometry and the physics captured by the expression, this awful thing. The expression appears when expressing the symplectic form in terms of position and velocity. There you go. Mathematical problem. The expression appears with the EM tensor in the spatial temporal part of the symplectic form when it is expressed in terms of position and velocity. It also appears as a correction for the raised anti-symmetrized covariant derivative. This means the expression should have both geometrical and physical significance, which merits further study. As an example of the type of things we're looking for, is expansion a tensor? I already know that the expansion is not a tensor, so that is not. How is it related to curvature? Is it always zero on flat space? Can it be zero on curved space? And we have part of these answers. How is it related to curvature? Is it related to curvature? Okay. So actually, the question is it related to non-inertial frames? That's actually the question. Is it related to curvature? Is it always zero on flat spaces? Can it be zero on curved spaces? Can it be interpreted as a gravitational force? Well, it also needs to be inertial. From calculation, the tensor can be understood as the difference between taking an anti-symmetrized covariant derivative and the anti-symmetrized partial derivative. What does it say? Know that setting is not really that of space-time, but the phase space. The general idea is to understand. So this is fine. And again, we have a video. for this, and I might as well add it. So it's kind of like where I'd like to be, where we have a list of open problems, and some of them have a video that describe what the problem is, and some people then uh, can look at it and see if they can help in some way. Okay. Very good. And so here, how much of relativity is already there in particle equation? Okay, following the convention set up in this thing, apply the Hamiltonian constraint of the symplectic form to see whether there is a dependence between the M field and the metric tensor. Yes. In the link node, we find the expression of the symplectic form in terms of position and velocity. The expression lives on the 8-dimensional space TQI EPI, which is redundant given the Hamiltonian constraint. And this is just essentially the form velocity, the norm of the form velocity. The idea is to use the constraint to lower the dimensionality of the form to a 7-dimensional non-symplectic form. Yeah, let's not call it a contact form, but to understand whether on that submanifold there is a relationship between A alpha and G alpha fields. The Hamiltonian constraint plays a double role. It is the generator of the affine parameter, time evolution, and is conserved during evolution, specifically the rest energy of the particle. What we want to understand is whether this double role puts a constraint on how these two fields can vary across phase space. If there is indeed a connection, it would mean that there are some hints of general relativity in plane particle dynamics. If there isn't, then the link between curvature and energy is a separate assumption from those required to derive particle dynamics and the scalar and potential forces. And this, I still have no good sense of which is the correct one. Okay. So these are much better than I thought. Sometimes when I do all the things and they sit there, I always reimagine them as they're worse than I remember or what they are. Find a better mathematical correlation for quantum states. Find a better physical motivated characterization for a state space of quantum mechanics. The standard way to represent quantum mechanics is using vectors in a Hilbert space. The recombinant over Hilbert space can be broken up into the following vector space: normed, complete under the norm. Every closed linear subspace is the range of a projection. The completion under the norm seems the only non-physical requirement. And on the other hand, I should link the paper here. On the other hand, the Schwartz space is a dense subset of L square, which seems to be suited as it is closed under Fourier transfer. It has a finite expectation as for all polynomial position momentum. It is dense over L square. There are a bunch of other things. It so Schwartz spaces on different number of degrees of freedom are not isomorphic. Okay, in fact, requiring the second feature means recovering a Schwartz space. And does the Schwartz space satisfy all other characteristics of a Hilbert space except the closure under the norm? If we just drop the closure under the norm, what do we lose? So this question is for the projections, right? This is the thing that I'm not so sure whether you can say that every closed linear subspace is the range of a projection. But if I can have an inner product, that should be the case. Anyway, those are the things that need to be fully understood at a mathematical level that I really have no idea. Does a Schwartz space satisfy all other characteristics? Okay. Oh, there was also that paper. What was it? quasi-completeness. Yes, this thing. Yes, so there was some guy that I even contacted that had explored this notion of completeness as an alternative of the completeness under the norm. So while I was looking at other things, I found this guy that claimed to have a different notion of completeness that had a much better property at a categorical level. And yeah, so it might be source of ideas as well. A better so I think this is yeah, mathematical. It has to be. Okay, and we should also put the link to their paper. See this paper, and then for more details, and that's going to be in research. Let me see. The physicality of the Hilbert space. There you go. Oh, I haven't been looking at the chat. Okay, no messages. Okay, so that's it. If you look at the first list of defining property of a Hilbert space, completeness is the only one that does not make physical sense. The linearity of the normed vector space can be understood as coming from the linearity of probability space. The existence of a projection is a requirement of being able to identify states. A measurement that occurs that up to one is the state if the state matches and zero if it doesn't. The completeness would mean that the limit of a sequence of state preparation always lead to a state, but this is not the case. You can in principle prepare states with narrower and narrower spatial distribution, but not zero spatial distribution, delta Dirac. The idea would be, okay, this is a bad example because this is not a limit in the Cauchy sequence. So let's say we can in principle prepare states with let's say with greater and greater spread in position, but not infinite spread in position. In general, if the sequence of expectation values for one observable goes to infinity, it is clear that the limit cannot be understood as a realizable preparation. Okay. Notes even listed all problems with Hilbert spaces may be useful. For example, a radar problem with Hilbert spaces is that self-adjoint operations that are defined on the whole space must be bounded. This means that unbounded operators must not be defined on all states. So there must be states for which the average position is not well defined. Again, note that this is not true for Schwartz space. For the Schwartz space, the position is unbounded. There is no maximum value for position, but all states have a well-defined average position. Okay, so I think this is.
Can I ask something about this?
Yeah, of course. You have to.
So you don't want to include the delta Dirac because it's not really in L2. Like it's not really a limit of like maybe Gauss functions getting like more peaked.
Right. So it's a limit, but it's not a limit that it's comes from the completeness under the norm.
Yeah, but if we have a Schwartz space,
Mhm.
we have a delta Dirac in the dual.
In the dual, yes.
So mm, usually in a Hilbert space, I don't need to worry about this. If I have a pure state, it's like the same as its dual or like equivalent to its
Yes.
dual. But now, if I'm really saying my states, my pure states are elements in the Schwartz space, what are then the dual elements? There are more of them. Are
Yes.
those?
The,
How do I interpret then the dual space?
so the dual space should just be the space of observables. Of,
Observables. Okay.
yeah, because the dual space is the space of all linear functions from the original space to R.
Yes.
Okay. So you can imagine that an observable is is something like that. It's something that takes any, well, caveats. Because okay, so there are a bunch of problems. Because first of all, the state space is not the vector space anyway. The state space is the projective part.
Sure. Yeah.
And so really the observables should be really defined on there. So if so essentially I wouldn't, probably observable is the wrong word. It's a set of essentially at an abstract mathematical level, it's the set of values that can be extracted from a state.
Mm.
Right. So I don't know that we should consider them observables in a quantum mechanics sense of Hermitian operators and all that. And the requirements on the observables are probably going to be more stringent because they need to be somehow continuous in the topology as well. And I doubt that the delta Dirac would have that feature anyway.
Yeah. And our Schwartz space, those are still complex functions, right?
Yes.
So our delta Dirac would like pick up um, the value of my function at any point.
Yes.
So that would be a complex number,
Exactly.
which
Yeah.
depends on the phase. Okay.
Yeah. So that's exactly what I was saying, that, oh, maybe, we have to be on the projective space. Once you are in the projective space and you have linear functions in the projective space, well, actually, it's not going to even be the linear function in the projective space. It's going to be in the linear functions on ensembles. Those are really the things that become observables.
Okay. So and actually our density matrices will then also be defined only on on the Schwartz space and not on the dual.
Correct. Yes.
Yeah, okay.
Yes.
Okay.
Yeah,
Uh,
so it's a whole thing that is up in the air. So the thing that I do not know is whether we can even do this, this particular subset of the problem, or it's just easier to create the ensemble space for all possible physical theories and see quantum mechanics in as a as a particular instantiation of that with particular elements, because. Um, because we have to go back to the drawing boards and understand what are the properties that we must have for physical states anyway. And that point, if we have to make those arguments are much more likely to be made in the abstract than on the concrete, because you have to say, things like, at the end of the day, physical theories describe regularities, describe things that we can always prepare and measure, and therefore there are about ensembles, because those are the things that represent the regularity, the fact that you have this infinite possible ways to repeat the measurement, right? And those type of arguments are going to apply to both classical mechanics, quantum mechanics, any physical theory anyway. So it might be easier to just make those arguments in more general and then find what is the proper restriction on quantum space.
I think that makes sense.
Yeah. So, but the problem still stands. Like Hilbert spaces are bad. We need something for quantum mechanics. Whether it's easier to find the specific for quantum mechanics and then the general, or first the general and then find the specific for quantum mechanics is just a matter of strategy, not of what the problem is.
Okay, and there is another question that I had. I don't know. It's related, I think, which was if I'm restrict myself to a Schwarz space and all my observables, all my operators are defined only on the Schwarz space.
Mhm,
So also my Hamiltonian. Uh,
mhm,
do I, if I then have time evolution generated by this Hamiltonian, which is defined on this Schwarz space, do
mhm.
I stay inside the Schwarz space or
Yeah. So we don't know. We should put it here as a question.
good?
If we have a Hamiltonian that is I can't say that it's a Schwartz function. Well, let's start saying that it's a polynomial of position and momentum. Does that map Schwartz functions to Schwartz functions? What is the constraint on the Hamiltonian such that the evolution maps Schwartz functions to Schwartz functions? We can also add what is the role, if any, of the dual space, because it could be that, now that I think it more properly, it might be that we're not really going to care about linear functions as being defined on the dual. We only care about linear function that maps a Schwartz function to Schwartz function, and maybe that's not the dual at all, because the dual is defined on the inner product actually. But the inner product is going to be the functions that I have no idea. Yeah, okay, so right, okay, so this is the thing. The dual is defined on, let's say, on the bras, right? So the set of things that map the space to the real number. But what we actually seem to be more interested in is the linear operators that map Schwartz function to Schwartz functions. And those are two different things.
And as you said, it might be easier to understand this in general when we have mixed states.
Yeah.
And then, so I've seen this one derivation. Um, what was it? Quantum Theory from First Principles, this book.
Okay.
I think I shared with you. You met one of the authors. I forgot the name. There were some Italian guys. I don't
Okay.
remember exactly,
Oh,
but
is it the Dariano's group?
yeah.
Yeah. Okay.
And there they do this, right? They start with mixed states, and actually the whole Hilbert space structure and so on, that it just drops out at the end, and it's actually looks quite unnatural.
Yeah. Okay.
While it makes more sense when you work with like ensembles and so on. Um, and then the specific case, like what it looks like on the Hilbert space, is really less intuitive than the more general picture.
But my understanding that they were doing it in finite dimension, right?
Yeah, sure, of course. But even
Okay.
there, um, the focus is on the mixed states.
Yeah. So there is a whole thing about the generalized probability theory. There are different people that have sort of looked on this, and they look at the convex space of mixed state. And in fact, I've been talking to one guy now that I'm trying to look at something. So the things that a lot of these approaches are missing, it's uh, it's basically the geometrical part that comes from the entropy. And if you are in finite dimension, it's not a problem because the finite dimension already sort of constrains everything anyway. And it's when you are infinite dimension that all these problems are going to crop up. And the entropy is crucial to tell you what things are finite and what things are infinite, essentially.
Is that the problem of how to, so for finitely many probabilities or something, you just add pi log pi.
Right.
You add this all up, you don't have a problem. And if it's infinite, you need some kind of measure if you want to integrate over all of your
Yeah.
over your probability density. Is that the problem you are
Yeah.
referring to?
It's related because that measure is going to be related to the entropy anyway. So if you think about in classical mechanics, the when you're integrating, you have to do it over conjugate variable and using the Liouville's measure. Otherwise, it's not going to
Yeah.
work. And what at some point, I don't know if I should start. We should start having discussions here on that on the ensemble spaces approach because uh, I've been actually doing a lot of progress there, and the existence of an entropy with particular bounds, with an upper bound and a lower bound, constrains a lot of things to the point that you can prove that there is only one entropy, that it has to be essentially the standard entropy that we have. And the trick seems to be that when you do convex combination, you always allow for finite convex combination, but not infinite. Because essentially the finite is the only one that you're always guaranteed to make. And then the entropy bound on how much the entropy can increase, you can find that it's really the Shannon entropy on the coefficient. And that's the same in classical mechanics and quantum mechanics. So the relationship of sort of the differences in entropy when you're mixing, it's always the Shannon entropy in the continuum or in the discrete in classical or in quantum. And that's enough to sort of fix a lot of other things. And a- and that's what allows you to sort of treat the infinite case as the limit of uh, the infinite case as a limit of the finite cases. Because what you're doing is you have an ensemble and you keep decomposing it, and decomposing it, and that's where you get the limits. But there are some pieces that I still need to get done, but there are a lot of pieces that are already done. And the other part that needs to be understood, but this is past. Yeah, well, there is a whole thing about this the symplectic structure that has to come out that I still that I think I made a progress this week and last week so that I know at least what I have to get mathematically. I don't know what's the physical justification, but anyway. Uh, Yes, so you were saying that they also find that the when you go to the complex vector space, things become a little bit more less natural, let's say.
I'm not sure if they are saying it. Maybe it's just me because that's the part that I understand the least.
Less. Okay.
Where just all of a sudden, yeah, there's you can define a Hilbert space, and then all the stuff you were talking about turns out to be operators on that Hilbert space, and
Yeah.
it works, but there's I don't know. I don't have an intuition for that.
Yeah. So part of this, as I said, I'm discussing some of this thing with Alex Wills, which is like a mathematician that did a lot of work also in quantum logic, and he also has done work on GPTs and on generalized probability theories. And he told me, I think I have notes here, that there is a general thing that if you have a vector space that it's radially compact, that has neighborhoods that are radially compact, absorptive, and balanced, then this becomes a unit norm on some other vector space. And I still don't understand fully what this means. But the point is that we should be able to satisfy those conditions at an abstract level on the generalized ensemble space. And these might be the thing that then allow you to say, oh, okay, I can understand these as you know, the space of trace one matrices in a Hilbert space and blah, 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 blah. And so there is a mathematical step that you are sort of that I think it will need to be abstract and less physically motivated because you're basically choosing a convenient mathematical representation. And that's basically it. Okay.
I think that's good.
Okay. So let's go to the next one. Oh, I should check the chat. Oh, okay, somebody. Hi, meme of distraction. I don't know when you chatted. Unfortunately, I need a pop-up. Can I get a pop-up with just the chat? Pop-out chat. I can do it. Oh, this is so much nicer. Okay, so now I can put the chat over here. Okay, so now I can see the chat better. Okay, so we got this. And next one, continuum hypothesis. Is the continuum hypothesis relevant in physics? Determine whether the continuum hypothesis can be relevant in physics. As part of the general theory, we have determined that any space of experimentally distinguishable cases forms a second countable T0 topological space. Therefore, we can ask mathematically whether there exists such a topological space where the cardinality of the set is more than countable but less than that of a continuum. As part of a general theory, we have shown that the cardinality of the set of experimentally distinguishable cases is the most of that of a continuum, as it must allow a topology that is D0 and second countable. The standard formation of that theory does not tell us whether sets of cardinality between countable and continuum exist, which is that a separate axiom. Given the physical premises, we should consider whether this chart is relevant for physics. For example, it may be that a set of all possible space-time events, the structure of space-time has cardinality that is between, and this is a complete fantasy, of course, has cardinality that is in between the countable and the continuum. The first step would be to understand whether such a set could be given a suitable topology such that each open set corresponds to an experimental verifiable statement, as is done in our general theory. Yeah, so this, I think it remains like this. And it's one of those things that I have absolutely no idea whether, and so I just leave it there. And hopefully some mathematical logician will come and tell me some stuff that might be useful.
So what is countable and what is continuous? Like the full set of statements, they're countably many, but second countable means I have a countable basis, right? That
Yes,
generates the topology. Mhm.
correct.
Okay. Why do we need to know the cardinality? I mean, maybe we just cannot determine it, or I don't know.
So let's see. The cardinality of the statements can also be the cardinality of the continuum. The cardinality of the base has to be has to be countable. And then what happens is that the set of elements that can be distinguished for a countable basis can only be up to the continuum. Now, if so right now, the only topological spaces that we have that we do physics on are things that are maybe discrete and up to countable, right? So that would be the number of, so the An observable like the number of particles would be that it's discrete and countable, or they are continuum like real numbers, right? If there were sets that were in between, we probably don't even can't really imagine how these things work or are, because those are the only two buckets that we have in our head. My hunch is that they're still not going to be relevant for physics, because when I've tried to look at constructions of how you get sets that are in between the continuum and the countable, it's like they're so convoluted that after the second or third step, I don't I get lost. There is something called forcing that it's used in set theory to construct these sets, and yeah, like I was never able to either understand it or somebody understand me how that works.
So the basis is that isn't it like undecidable in ZFC whether there
Yes,
exist these things or not?
Yes.
it is.
So there are like, I guess I could just find another axiomatic set, like add an axiom, and then it tells me they exist
Yeah.
or not.
Yeah, and that's precisely what they do in forcing. They create a model of ZFC where the continuum hypothesis fails. So it can be shown mathematically that you can actually construct these things. So not only that the sort of ZFC tells you nothing about the issue, but you can also create something where the continuum hypothesis is not satisfied. So you can provide an example of a construction.
So in a more powerful system, you prove the existence of such a set with a cardinality in between, but ZFC alone would not be powerful enough to say whether this exists, to prove whether this set exists in ZFC alone. Does that make sense?
Right. So basically ZFC is agnostic. Like it's not a problem of power or not power, because the axiom of ZFC, yeah, there could be such thing or there could not be such thing. It's not committal.
I mean, that is a matter of power, right? A more powerful theory would distinguish between those cases where CFC cannot.
I guess then we just arguing what do we mean by power. But yes, so if you have more axioms, if that's the power and it tells you more things, then yes, agreed.
I guess I don't see yet what we would gain from from distinguishing those cases. Why does it really matter to this endeavor?
So wait, there is a chat. Jacob found that we can use non-Markovian dynamics for quantum theory, framing it as a yeah. So I'm a little bit aware. Okay, a couple of years ago he gave a presentation and I looked at that. I don't think that though there is an issue of cardinality for non-Markovian dynamics. Like I think that's a separate issue. In fact, I have no idea, for example, whether one can create a measure theory on these sets that are in between, quite frankly. I have no idea. Anyway, so Mark, what were you saying that you didn't understand?
I'm not quite sure why it matters yet. Why it would be a pretty big step to basically upgrade your like I'd rather be inclined to reduce axioms where possible and not necessarily add additional ones if it's not absolutely necessary for what you're doing here.
Completely agreed. The question is whether I can say it's whether there exist physically interesting theories in which this can happen. So my hunch is that one might be able to say, ah, no, you can't do it, right?
Yeah, I think probably, yeah, same.
Right. And but then it would tell us something strong because it would tell us, look, if you are not looking at all the set of possible mathematical theories, but you're only looking at the ones that are interesting for physics, then you basically say, oh yeah, then we can safely assume that the continuous hypothesis because this is never going to happen. Like quite frankly, it just occurred to me right now by looking at the comment on Markovian dynamics, right? It might be that if you're trying to do something like a measure theory, so therefore a probability theory on a set, it might be that there are some things that makes it so that you can't have you can't do it on sets that are in between the two cardinalities, right? And if that thing is true, then already would tell you, yeah, that's one reason why you can't do it, right? It's just that to me right now, it's just a hunch that you're not going to be able to do it or it's not going to be interesting. And since we were able to rule out all sets that are cardinality greater than the continuum, right? It would be nice if we could also say that we rule out all the cardinality that is in between the continuum and the discrete and the countable. Because then we know that there are only three things we're ever going to care: the continuum, the countable, and the finite, and that's it.
Mm-hmm. It might be that that's exactly undecidable because the continuum hypothesis is undecidable.
Yeah, I don't know. But there's still going to be whether there is an experimentally testable theory that for which the number of cases are in between.
Yeah, makes sense.
It could also be that even if it existed, you are not going to be able to distinguish it from one that has the continuum, right? That could be even another argument. So at that point, since you can't distinguish between the two, you might as well just use the continuum. Yeah, so it's basically, as I said, it's the question that we have no idea what more or less I'm talking about, but there has to be something in this space that needs to be made more clear, I guess.
Can I maybe try to summarize? Because so you said we have a bound on the cardinality of the set of statements, right?
On the set of possibilities.
Set of possibilities?
Yes.
Okay, but it's the continuum, right?
Yes.
And you're saying, okay, I at least have this bound.
Yeah.
But in principle, then there could be something below that. And
Yeah.
If it's really below, in the sense it's countable, then I know this is something that I can handle with ZFC, like the normal axioms. But the bound doesn't tell me whether there might be something in between, in principle.
Mhm.
And then I know that I basically cannot use ZFC, right?
No,
If
you
there would be a physical theory where I know that the set of statements has cardinality in between these two, which could just randomly happen, like our bound would not exclude this, then I would need something else, like a different set of axioms, right?
No, you can still use GFC, even if you have a set that the cardinality is in between.
Yeah, just need an extension of CFC. Like just that one extra axiom that tells you, yep, there can be
Sure, but this
stuff
is not
between.
ZFC anymore. It's really a new axiom. I'm just
yeah, sure. It's an extension of CFC in that like everything that CFC proved that would still be true in there because the
That's
continuum
true, yeah.
hypothesis is independent of CFC.
But is it really the thing we are worried about, that we might be forced for some physical theory to extend ZFC by some other axiom so that I know basically that I can prove the existence of our set of
No,
possibilities.
no, that's not my worry. My worry
Not?
is that currently all the models that we have are either have countably many possibilities or they have the cardinality of the continuum. Those all the models that we have right now, the physical theory that we are one or the other, right? And so the question is, well, what if the theory that we need at Planck scale, and I know that I say something that could be completely stupid, right? Suppose that the theory at Planck scale was neither had, the possible cases of a theory at Planck scale was neither countable nor has the cardinality of the continuum. Could we have that?
Is it just out of curiosity? I mean, that would be kind of interesting because it's very different. But what's the problem we would encounter? Is it the fact that ZFC couldn't prove that this set of possibilities exists? Because
Oh, the problem is that we need a different theory. It's not a problem of ZFC anymore, right? It's the type of space that we we always, oh, we have Rn. No, we're not going to have Rn. Oh, then we have Z. No, we don't have Z. We have something else.
okay, so it's not necessarily with the axioms of set theory.
It's not
More
the
general.
axiom of set theory. It's the objects that we use to construct our physical theory, right? So as soon as you assume that all the observables that we have, whatever, are a real number or integers, then those are the only two things that we allow our physical theories to have, right? And so the question is, can we have something else? And quite likely it's going to be no, also because with the work that I'm doing on the generalized ensemble space, it happens. I can basically show that the space of of ensembles, it's always a real vector space. As soon as you say, oh, I have things that mix and I have an entropy, right? Then whatever those things are, it doesn't really matter. I'm going to have a real vector space, right? So if that is true, and if we always need the entropy to describe ensembles, and that's it, this question is basically, I think it's moot. I guess I don't know, but I think it should be moot because it's just going to be an infinite manifold with boundary, and then at that point, the boundaries, I don't think they can be something weird. So, but again, I don't know.
So I guess the vector space structure that you were talking about comes from the fact that probabilities are real numbers.
Yes.
Okay.
Okay. Yeah. So it could be that the probabilities when you do mixing, but I don't know. I don't think those can fail to be real numbers because they are limits of the ratios, and so they are going to be real numbers. So yeah. So as I said, this is more of a mathematical curiosity. And it's more, I think, my hunch is just to be able to close this loophole more than have something that is actually physically interested. But a lot of the time, when you try to close loopholes, you find that there are actually some either hidden assumption or that you can't actually close. So does it make sense?
Okay, but really the problem would be that if something like that exists, we need something with cardinality in between.
Yes.
We would have a hard time constructing this stuff.
Yes.
Okay.
And so if we need it, we are going to need a significantly different mathematics from what we currently use. Most likely we don't need it, but if we need it, that would be the case.
Which also begs the question how we would even find such an example for a theory. Because we don't have the tools to construct this kind of thing.
Well, they have some things that, as I said, in set theory that I don't quite understand. The only way that I can sort of that I can sort of understand this is if you start with some countable bases of a verifiable statement, right? But these statements are highly dependent on one and the other, such that because again, you can still imagine, right, that all these points are still going to be a string of bits, a countable string of bits, no matter what. They have to be, right? So the only thing that can happen is that you have such correlations between the bits that you get that that you get, you know, when you go and count them, you get something that it's in between, let's say the real numbers, where you can kind of have at some point some no correlation anymore, so that you can get some sort of I wouldn't say all the permutation, but enough permutations. And then you think the rationals start becoming periodic. So you have sort of, and not only you have total correlation after a certain point, you have something that you know that is cyclical. Like once you know a finite string, you can see that it's always the same. And so it could be that there is something in between, right? That this string of bits they don't start repeating. But they don't really explore too many things. They sort of become more and more constrained as you go forward. And again, I have no idea whether this that I said makes sense or not.
I think I understand it as, in general, if they would be uncorrelated, you have finitely or countably many, possibly infinitely, many bits. So then your whole number of words using these bits is infinite.
Mhm.
Even continuous, right? Those are the real numbers.
Yeah.
And then you say, but if they're correlated, then actually I don't have all of these words because some of them are like redundant. They are essentially the same.
Yeah.
And you could restrict this if you have lots of correlation restricted to countably many. And if you have no restrictions, you would have continuity, and maybe something in between would give us something, yeah, also with cardinality in between.
Yeah.
That makes sense. Okay.
So another way that I can sort of think it in a information theoretic way, right? So you can imagine if I have this string of bits and at some points I start repeating, then it means that at some point the new bits give me no new information, right? If I imagine on the continuum, every new digit will gonna give me some more information, which you can imagine that it's in some level constant. And so you could imagine that you keep getting new information, but you can keep getting less and less and less. And I don't know whether that case, for example, would go in between. Again, it's all speculation. Okay, WWKK says Wolfram Mathematical Project also concluded that if you have integers, you won't be able to escape irrationals no matter how hard we try. Yes, so yeah, I have no idea even if if you can define rationals or irrationals on these sets that are in between. As I said, like it's completely out of my depth in how to really understand this. And again, it could be that if I talked to an expert and he told me some things, I would say, "Oh yeah, okay, this is never going to happen because of something very obvious." But right now, I don't see it. So that's why it's an open problem. I'm basically fishing for somebody who knows this thing and have a chat. So if anybody knows somebody who knows these things and wants to entertain these discussions, we could even have it organize it here on the channel and see how far we get. Okay, enough about this. Next, review logic axioms. See whether the axioms of logic can be reduced and they put it in a form more palatable to a logician. The correct formulations define the context is a set of propositions of potentially any cardinality from which a countably generated subset is extracted. Part of the reason is that it was hard to find mathematicians that were able to tell us precisely what are the conditions for closures. To be safe, we specify closures as one of the axioms. Since in the end, the only closure that we will need is under countable operations, it may be possible to bootstrap the system simply with a countably generating height in algebra, which represents a closed set of verifiable statements. So this requires that any height in algebra can be embedded into a unique countably generated sigma algebra that point the concept. Okay, so this is just a different way to construct the same thing. So it's really, really low priority for me, unless there is, as I said here, somebody from the mathematical logic that says, oh, actually, if you put it in this way, logicians are going to be more interested. So currently the idea is that we start with a logical concept, which is a set of all statements we may want to make with within a specific theory. The physically meaningful statements are a subset of constants. For example, the context may contain statements that are not experimentally verifiable, but when constructing experimental domains, these non-distinguishable possibilities merge together to match the resolution provided by the statements. The proposal here is to start only with verifiable statements. What needs to be understood is whether the logical relationship defined on the verifiable statements are enough to infer the logical relationship on all theoretical statements that can be generated with countably many operations. The existence of a unique closure would also guarantee that we're not accidentally ruled out some theories, and that theoretical statements can always be understood to follow the law of excluded mill. Yeah, again, this is just a technical thing, again, to close to dot the I's and cross the T's. Not so interesting. Relativity as integration. This is the thing, Tobias, that we discussed it at some point. So see how much of special relativity can be recovered by positing spatially integrable distributions for all inertial observers. The idea is that while space and time variables have the same role when identifying an event, their own coordinates, they play different roles under integration. If we have a probability distribution, for example, the constraint is not the integral on both space and time equal 1, but rather the integral over space is equal 1 for L surface U at equal time. A boosted observer will see time and space mixed, but the constraint will have to apply at equal time for the boosted observer. Alternatively, the distribution can be assumed to be in position time velocity, as this would be the variable needed to specify the initial conditions. And so the physical significant here is the goal is to remove the postulate of the invariance of the speed of light. The ability to express constraints such as unitary probability in a coordinate-independent way would be a requirement for the principle of relativity itself. The idea is that integrating in time versus space becomes relative to the observer, and therefore there must be a unique way to change units of space into time. The speed of light then would not be a speed, but the constant that translates time interval into spatial intervals, i.e. it is the ratio between the measure on space and time. This I still think that it has to be true, and if we find the right trick, it's gonna be trivial. And but yeah, so this is this is one of the open things that I'd like at some point to get done.
I posted a paper for that in the Assumption of Physics Discord.
Oh, let's see.
I think it solves all the problems though, but it's maybe at least a partial answer.
Okay, quantum reference frame from Lorentz symmetry. But this is quantum reference frame.
Yes, I thought we were on the this general stuff, not just quantum. Okay.
No, this is just the integration, so it's completely
Okay.
mechanics.
Never mind. Might still be interesting, but not for this. Okay, got it.
Yeah. Oh, you also put something about the reals.
Yeah, I'm not sure if that matters, but I just put it there quietly because I thought that may be better looked after.
Okay, I'll look it after that. Yeah, so this in principle should just be the fact that when you do a coordinate transformation, right, this dx that you have as an integration on one observer becomes a dx plus dt for another observer. So when you're making these translations, you are going to have to change an integration in space to an integration of time, and this integration of your probability evolution will need to integrate in 1-to-1. And this should be the fact that you're not going to be, this is where a picture would be useful. So if you imagine a probability distribution going up, forward in time, you have a uniform distribution, and then this goes forward in time. At some point, if you keep cutting the distribution more and more slanted, at some point you are going to cut the distribution along the vertical line or too close to a vertical line, and then things are going to add up more to 1. And so I think this constraint will do a lot more than one think. And so I would think that there has to be something. But again, I haven't sat down to work out the math just because I don't have time to work on all the cool problems. I'm doing other stuff right now. But this is I still dear to my heart because I think the intuition is going to work. Okay, then quantum states as equilibria. Determine whether quantum states are stable equilibria. Don't remember this one. For a measurable process, small perturbation of final states yield back the same state or not. If a process is modeled by a projection operator, the eigenvectors of an operator are equilibria in the sense that they are those vectors and only those vectors that are unchanged by the process. We want to determine whether those equilibria are stable, that is, whether small perturbations of those vectors project to the same vectors. Yes. The general approach, I completely forgot about this one. The general approach we have, and that's why I have the list. The general approach we have to quantum states is that they represent an equilibrium with both the environment and internal process that act as a higher time scale. For example, the proton can be understood as a single quantum object precisely when we can neglect its internal dynamics and the coupling of the internal dynamics with the environment. In this sense, the system is at equilibrium. A measurement then is a process with equilibria where each equilibrium corresponds to a particular measurement value. A difference from the thermodynamic case, though, is that the final state is not fully determined by the initial state. The initial state only sets a probability distribution. We want to make sure that, at least for small perturbation, each final states recover this property. Geometrically, this seems to be the case, since the only way to make change to a unit variation is a rotation, which for small changes is a change in the perpendicular component. This means that the small perturbation of the projection should push back the vector to the original one. Yeah, so this should work, and it would give us the idea that all states are indeed stable equilibria. Okay, yeah, this I forgot. It shouldn't be hard to prove, and yeah, it needs to be done. Relativistic spin. This is something also that I never. Provide a classical analog for spin that works relativistically. In Hamiltonian mechanics, the phase space of a free particle is given by the conjugate quantities Q and P, and the Hamiltonian 1/2 m 1/2m p squared, essentially. In the extended phase space, the variables become Q and P, but with the alpha, and we have time and energy, and the extended Hamiltonian is 1/2 p squared. Note that the extended Hamiltonian functions both as a constraint as the generator of the affine parameter, proper time for particles and minus proper time for antiparticles. If we take a spatial direction as a degree of freedom, phase space is the two-sphere, the only sphere that is also symplectic manifold, identified by all unitary vectors of component Si. The conjugate quantities are given by the angle over a plane and the component perpendicular to the plane. For example, we have the theta xi and sz. And if you do the Poisson bracket between these two, you get to 1. Yeah, but this, I guess, this should be what we would like to have, right? Let me go in the... Yeah, I want to say this equal to 1. That's kind of the point. That's how you know that they're conjugate. The Hamiltonian is given by that. The problem is to find the correct space and correct conjugate variables for relativistic case. It is that the spin is in quantum mechanics is the quantization of directional degree of freedom. It is not clear whether the correct generalization is a direction in space-time or a plane of rotation in space-time. In the first case, we would expect spin to generalize to a 4-vector, while in the second case to a 2-form, an antisymmetric rank 2 tensor. The other issue is to fully understand how the units work. In the same way, the conjugate momentum is covariant under changes of position, as should be covariant under changes of angles. Somehow, radian units for angles are better. For 1, if we take units of radian for the angle, the range of the angle is 2 pi. If we take the range of a z, then it's h bar over 2 and 2 minus h bar over 2. And since then the area is equal to h, which is the sort of the lower bound on areas in phase space. Therefore, if we have a sphere with a surface area equal to Planck constant by using radians for angle, we find the range of spins a vertical component to match that of spin 1/2 system. So this is, there are a lot of things that I still don't understand about spin. And what I would hope this would tell me is why we have the spin statistics theorem, because I still also don't understand that. Yeah. Okay. Then the quantum moment problem. Determine the correct equivalent formulation between classical and quantum moment problem. And this is still, I do not understand. In probability theory and statistics, the moments of a distribution over a stochastic variable x are the expectation values mi e of xi and all the powers of x. The moment problem is determining whether, given all the moments of the distribution, one can reconstruct the probability distribution. That is, given a sequence mi, determine whether a positive Borel measure mu exists such that you can always see the expected those mi's as the expectations. Note that not all sequences of mi allow for a solution. In general, the moment problem may have multiple solutions. 2 different probability distributions can have the same moments. The multivariate case does not seem to have a clear solution. In quantum mechanics, there is an analogous problem which aims to reconstruct a mid-state from expectation value of observables. For example, one starts with mij, the expectation of position and momentum, and tries to find a suitable rho such that we have actually this. I should probably symmetrize it. Otherwise, it doesn't make much sense. And tries to find a suitable rho such that the trace... Oh, okay. Fair enough. I already had it. The symmetrization is when I do the this. Okay. Alternative 1 can formulate the problem in terms of quasi-probability distribution on phase space. Now there are multiple representations since there is no single product of observable. Therefore, depending on what permutations are chosen, one gets different quasi-probability distribution. It would be nice to have a summary of these details. The Wigner function should correspond to a choice where the product is defined with all permutation. And one can now ask whether there are moment values that can solve both problems. This essentially is asking whether there are quantum expectations that give a semi-definite Wigner function. In general, question seems to not have an answer. For pure states, it seems that only Gaussians have semi-positive Wigner function. I don't even know if the moments of a quantum Gaussian states match the one of a classical Gaussian state. This would also be it would be interesting to even see whether the moments of a quantum Gaussian state match those of a classical Gaussian state. Yeah, so this is something that I would be totally curious to understand because it also relates to the classical limit. So what it seems to have to happen is that if you are at low entropy, you can't solve both problems even as an approximation. And then when you go to ensembles at a high entropy, you should be able to solve, with a smaller and smaller approximation, you should be able to solve both problems, the quantum problems and the classical problems, but you should never be able to solve both at the same time. At least this should be my intuition. And it would be nice to know whether the intuition is confirmed or not. Another interesting aspect is that pure quantum states always solve the moment problems uniquely, as their topology is induced by the semi-norms defined by the expectations. Given that pure states have zero entropy, a possible equivalent in classical mechanics would be to ask whether the moment problem is uniquely fixed once a set value of entropy is given. Yeah, yes, old me. That's a nice thing to look at. Given that the solution to the moment problem for both classical and quantum mechanics exists only for Gaussian, is it? I have no idea. I have no idea whether this is true. Oh, it would be in, okay, it's because the Wigner function of a Gaussian state is a Gaussian. And therefore, it should actually work out.
So I think for the Fourier transform, the eigenfunctions are like Hermite functions, right?
Yes.
And then there should be some equivalent for the Wigner functions. And only the Gaussian is all positive, right? Because the others would fluctuate below, but maybe some linear combinations of them would.
Yeah, linear combination should wait. No, you do the linear combination of the functions, the expectations are gonna be nonlinear. So I don't know. So many things I don't know. Oh, jeez. Yeah, I can't. Okay, but this so interesting. Now, another thing about, okay, so if a Gaussian is still a Gaussian for the Wigner function, then yes, the moments, it's not really, would be interesting to see, would be interesting to double check. Okay, so now what is this? Given that the solution to the moment problem for both classical and mechanics, it should be clear that complete hidden variable theories has to be ruled out. However, it would be interesting to understand exactly how and why. As for the classical limit, we would like to show once the entropy tensor field is become classical, this would mean that the moment problem would be approximate. Yeah, I already had this insight back then. Yeah, and I still have made absolutely no progress in terms of this. So yeah, there is this is where again we go back to what Tobias was saying before, right? The Hilbert space formalism does a bunch of things, but it doesn't really bring out the essence of the problem. And I think this type of looking at the problem brings out the essence that you have statistical distributions that in principle are identifiable by these expectations, but then the expectations do not quite match. And then we still have the problem of the product of observable, which is the next one, that since you, like, why is it, so if this is true, that the moment of a quantum Gaussian magnitude was of a classical Gaussian, it is true only for a particular ordering. Because if you change the ordering, I would assume that the moment, the expectation of the moments would change as well. So, oh, we're starting to get late, so we have to get a cutoff. We can, yeah, we can do the next one because it's related, and then we'll stop. Product of observer. Omega decisive argument as to whether the. So it's not that it's not well defined. I want to understand what are the product of observables with a different ordering. What do they represent physically? So what do the different ordering of product represent physically? Then the other thing that I'd like to have, if I have three random variables, can I tell, or how can I tell whether one is the product of the other two? Like even these things I don't understand. Like, can this be understood as in terms of like a generated transformation, commutation of operations? That's basically my issue. Okay, so what did I write? This probably is something I will want to change. Okay, let's see. Thanks. I love the way you pose that question. I still like I can't understand, like, this is something like the many people see as the crucial thing, the fact that things do not commute and therefore you have multiple products. And we are still here, like 100 years later, and I don't think we have any clue of what this thing is. Okay, so given that the product of two self-adjoint operations is not necessarily self-adjoint, the question is whether there exists a canonical way to create a product of two quantum observables, or at the least to understand why there are multiple ones with different ordering. The issue is related to to positing a sigma algebra of observable, which is the starting point of the algebraic approach to quantum theory. The idea is to understand both at the mathematical and physical level what the product of observable is and why it is unique. By the way, this is exactly why, you know, a lot of people that do algebraic geometry, you say, oh yeah, you just have a C-star algebra and all that. And if I don't know what the product is, I don't even know what the algebra represents. And so I don't even, I can't even take that as a primitive from the physics, because I still don't know what I'm talking about. So the problem can be seen from two directions. How should we construct the product and how the product can be identified? For example, consider the sum. The sum of two self-adjoint operator is itself self-adjoint, so we have a straightforward way to construct it. Moreover, given two observable A, B, and C, we have C equals A plus B, if and only if the expectation of C is the sum of the two expectations for all states, so that we have a straightforward to identify that. Yes. For constructing the program, note that the function f applied to an operator corresponds to the self-adjoint operation, where the eigenvectors are the same, while the eigenvalues are different, are given by applying different function to related eigenvalue. Therefore, A plus B as a function of A Therefore, A plus B and function of A are allowed. And now we have the product is just the difference of the squares. The left side is in terms of operations that are allowed. Therefore, a product consistent with those rules must be in terms of the anti-commutator. The issue is that the operation so defined is not associative. Okay, so that if we do first the product of AB and then the product of BC, we get some commutators here. However, for position of momentum, we have that the commutator is a constant, and so the product is associative. But recursively applying the product, we would seem we are able to construct a polynomial of Q and Q, and therefore, are there any problem? Yes, because because there's still the non-commutations. So why do we have different permutations and what they do represent in terms of this canonical product? Okay, so for identification in terms of properties of expectation value, it is not clear. It is not clear for a generic function of one observable either. Exactly. Okay, so I already did mention these things. Ideally, we would like to say that an observable is a function of other observable if the expectation of one has some property with respect to the expectation of the others. This is the thing that I'm absolutely missing, and I need it also for the ensemble space, because even when I create this ensemble space, I can define that there are these essentially variables that are linear with respect to the convex combination of ensembles. But I don't know how to say that I have products and functions. I really don't understand how to do it. This is a problem that it's sort of fundamentally I still don't understand, and I need to. This would seem like a basic problem. They should have a settled question in the literature, yet we're not able to find in-depth treatment. The operation is well defined. It would also be interesting to understand what symmetry it would generate and what conjugate variables would be. If not, it would be interesting to know exactly the root of the problem, right? So, yeah, I still don't understand any of this. WWK, I completely agree with you. I tried to study the problem by trying to come up with a theoretical unitary anti-commutator operator to see why it should or should not work. Yeah, even if I just understood. Even okay, so let's simplify the problem. Let's say that I'm doing classical things. So I have a product, and I will have a conjugate variable of that product. What is the conjugate variable? So if I have position and momentum, right? Those are conjugate. Make the product of those two. What is the conjugate of the product? That I think already will be an interesting, simple problem to solve.
So how I understand the lack of commutativity as of right now is that it's basically the influence of the measurement on the state in a way, right? So in classical mechanics, I think stuff should be commutative.
Right, but so there are two things. One is the commutator relationship in terms of yes, what you said, the uncertainties and effects and stuff like that. But in classical mechanics, you still have the Poisson brackets, and the Poisson bracket match the structure of the commutator, right? So in terms of generators of transformations, the structure, at least for the Q and P, is the same. So what is it? You see, if the structure for P and Q in both classical mechanics, in both classical mechanics and quantum mechanics, the Lie algebra that you put on these observable is the same. How is it that then when you do the products, you start getting something different. Like, what is it that it's actually different in terms of that? And it's in some sense, it will need to be related to the fact that we can't reduce the uncertainty between position and momentum in quantum mechanics to whatever we want. But if it's really just that the case, we could just look at the subsets of statistical distribution in quantum mechanics that have zero entropy or above. Because if we make that limitation, we are going to have an uncertainty principle in classical mechanics as well. But I don't think that just that warrants the fact that we have multiple products. So what is it exactly that gives me these multiple products? I don't know if I was able to articulate that.
I'm not sure.
So there is a sense that if you imagine that you have points, for example, then you can, in principle, reduce these things to points, make the product there, and then reintegrate, right? And maybe it's the fact that you can't do that in quantum mechanics that gives you these problems. So alternatively, like one thing that you can think of is that a classical statistical distribution can always, like if you have a point, then every value is uncorrelated. Every value of the marginal, every distribution in the marginal is going to be uncorrelated to every other marginal. You can't have correlations because everything has a point, right? If you have a distribution in classical mechanics, you can also have the correlations, and so it's not going to be true that the expectation of the product is a product of the expectation, right? But the fact that you can decompose everything into product, you can do it for the point, and then you reintegrate up. And so the idea is that in principle, you can shrink things and see it as a probability distribution over things that are uncorrelated. And maybe that's the thing that in quantum mechanics you can't do. You have, if you have a correlation, let's say, between position and momentum when you are at a pure state, you can't see that as a probability distribution of things that are uncorrelated. So that there is some kind of intrinsic correlation that you can't, wish away. And then maybe that's gonna give you the different product because you have different way to characterize these correlations. I have no idea, but there has to be something.
Yeah, that makes sense.
I should write that as a note somewhere here. Physical significant. One possible source of the problem is may relate to correlations. If two distribution, if two variables are uncorrelated, the expectation of the product is the product of the expectation. In classical mechanics, if the two variables are correlated, we can still see them as distribution over points, and the points, since they define all values with certainty, can be understood as having uncorrelated values. Therefore, in classical mechanics, every distribution can be understood understood as a convex combination of distributions that are, at least in the limit, uncorrelated. This cannot be done in quantum mechanics. Whether this is a useful insight or not, I still have no idea. Okay, so I would close it for now. If there are people that have questions or anything, I will open it to questions. Otherwise, we can adjourn. And while I wait for questions, I will make sure that everything works and push the changes. Okay, so this is the website, and this is updating list of files. Okay, pushed. Thank you, WWKK, for joining. Okay, so I don't see any questions. We'll just adjourn.
Okay.
Bye, guys. Thank you for following.
Bye.
See you next time.
Bye.
Where is the button to stop the live? There you go.